right, so this is now. This is right now is what's going on. So we're starting out with our 120 grams, right? And so what does that look like? Well, let's say it's this amount of carbon-14. It's a radioactive material that disintegrates slowly, right? And the half-life is 5,770 years. That means in 5,770 years' time in the future, right, there will be half of it left. So what's half of 120? Right, yeah. And so instead of this big lump of carbon, we'll have about half. We'll have just this left. That make sense? So we started with this, and now there's only half of it left because half of it has disintegrated over time. It's a radioactive substance that disintegrates over time. That make sense? And that's one half-life. Okay, so after one half-life, we've got 60 grams left, right? So after another half-life, there'll be half of it left again. And so half of that again would be like just this little bit, right? So how many grams would be left after another half-life? 30, good. And how many years later would that be? So, yeah, so 60 grams was 5,770 years. That's one half-life. So another half-life, see, every half-life takes this amount of time. So another half-life is going to be how many years? You need a calculator for it. It is, yes. Good. It's 5770 times 2. 11,540 years in the future. Good job. That's when that's two half-lives, and that's when we're left with 30 grams. Okay? So then there'll be another half-life. And how much will be left? 15 grams. Good job. And it'll look like this. Just a little bit, right? Half of the amount again, right? And how many years is that? How many years before we get all the way down to 15 grams? Yep, exactly. So if we take a half-life, it's 3 half-lives. So this is the first one, that's the next one. And then 5,770 times 3 gives our 17,310 years. Good. So let's do another half-life, a fourth one. How much grams is left? 7.5 grams left. Good job. And how many years ahead is that? And it's just this little bit left, that's all, because it's half of the previous amount, isn't it? Yeah, good job. So for 4 half-lives, this is 5770. Oops. Times 4. 23,080 years in the future is when we'll have 7.5 grams of carbon-14, right? And so on, right? So we're seeing the pattern, right? And we're getting the idea, right? So one way to come up with a kind of a formula to get these numbers, right? And if we said that T was the number of half-lives, which I think is what we do. So what will we have left after T half-lives? So in actual fact, let's not go to T. Let's go to like yeah. So like if we were to figure out, okay, how much have we left after, let's say, 10 half-lives, right? You know, is there a formula that we can get? Because this number keeps getting halved each time, right? So like to get from 120 to 60, we multiplied by a half, right? So we went 120 times a half, and that gave us 60, right? That makes sense? Right? Now to get to 30, we multiplied by a half again. So we did 60 divided by 2 and we got 30, right? But the other way is, what if we did 120 times a half? What's 120 times a half? 60. Yeah. And what's 120 times a half and then times a half again? Right. Because that's 60 and then times a half, that gives us 30, right? So to get the 30, we could do 120 times a half squared. Does that make sense? Now to get the 15, we could take our 120 times it by a half, that's 60, right? Times it by a half, and that's 30, isn't it? And then times it by a half again, and that's 15, right? So 15, isn't 15 just 120 times a half cubed? Isn't it? I'm going to plug that in the calculator for fun, because plug in 120 times a half is just 0.5. So 0.5 to the power of 3, right? Plug that in the calculator to see what we get. Right, does that make sense? Times 0.5 to the power of 3. Alright, it's 15. Good. Alright. And 4 half-lives gave us 7.5. So how would you... what formula can we do to come up with 7.5? Exactly. Just put it to the power of 4. 120 times a half to the power of 4. Or in a calculator, just for fun, go 120 star times 0.5 to the power of 4. Right? And see what that gives you. 120 times 0.5 to the power of 4. Right, cool. So, skip all the way to 10 half-lives, and how much have we got left? What formula could we use for this? Right, yeah. Go ahead and figure out how many grams remains after 10 half-lives. So 120 times a half to the power of 10. It's going to be very small because it keeps it'll be a very small number. That's okay though. And in a calculator, like I said, 120 star 0.5 to the power of 10. Yep, and we'll round that to the nearest decimal point, so we'll call that 0.1 grams. Right? So about 0.1 grams. And how many years is 10 half-lives, by the way? Good job, yeah. It's this 5,770 times 10, so just 57,700 years. Perfect. So just for fun, after, let's say, 23 half-lives, figure out the grams remaining and how many years that has been. Good job. Right. So good. So for the amount remaining, it's 120 times 0.5 to the power of 23. Let's do that. 20 times 0.5 to the power of 23. So, yep. So that's, I'm going to go 0.1234, 1, 2, 3, 4. And we'll just call that 14 grams. We'll round it to there. So not very many grams left. And that's rounded to, let's see, what's that? 1, 2, 3, 4, 5, 6 decimal places. So round to 6 decimal places in grams. And then, yeah, you just go 23 times that. So you're 5770 times 23, and that's the amount of years. 132,710 years, right? Now, the way radiocarbon dating works is kind of backwards, where we find something that is this amount of grams of carbon-14 when it would have been 120 grams of carbon-14 if it was now. You know, like if it was like, so let's say you find a fossil, or you find let's say you find some type of a cave where there was prehistoric people living, and you figure out that, wow, there should have been 120 grams of carbon-14, but we find there's only this amount, right? And when you measure that, you go, and you use this formula base, you go, oh, that was 132,000 years ago, right? You know what I mean? So radiocarbon dating, so in this example we're saying now we have this amount of grams, right? Imagine we have this amount of grams now, but radiocarbon dating is actually where they find a little amount of grams, and then they figure out, oh, that's how old it is. Does that make sense? Right, so anyway, that's just a summary. But so good deal. So the question then is, after T half-lives, how much have we got left? What would the formula be? Correct. 120 times a half to the power of t. And that is correct. That's the answer. Yep. So that is the formula for the amount remaining, right? Now, so the next thing we need to do with this is go, well, hold on a second. What if the years don't line up beautifully like they have been doing, right? What if we had an amount of years that was something like, let's say 7,000 years, right? 7,000 years, right? Now, 7,000 years is how many half-lives? It's more than one, isn't it? Because one half-life is 5,770 years, isn't it? Right. But it's less than 2. So take a guess. It's something like 1 point something. Isn't it 1.2 or 1.3 or 1.1? Does that make sense? So 7,000 years, guess how many half-lives it is? It's less than 2, isn't it? Right, it's something, right, it's 1 point something, right? So it might be 1.2 or 1.3 or something like that, right? But how do we figure out how many half-lives 7,000 years is? Okay. Well, let me show you and see if it makes sense. What if we did this? What if we went in your calculator, go 7,000 divided by 5770, right? What does that give? Right, approximately 1.2. Does that make sense? So it's about 1.2 year. It's about 1.2 half-lives, right? Now, because we're putting into a formula, we should probably. So I'm just going to say, okay, it's about 1.2. But because I'm putting it into a formula, I'm probably going to use this entire thing if I can, right? But in any case, so if I have 1.2 half-lives, then I go 120 times a half to the power of 1.2, correct? Right. Or in fact, let's just use some more digits because we want to be a bit more accurate. So we'll go 120 times 0.5 to the power of 1.21317. Yeah, I mean about there is good, or maybe I'll go 1.6 or something like that, right? So I'll just give it a bunch of digits just to be accurate, or even better on the calculator I can go 100. I've already got this in my calculator. I can go 120 times 0.5 to the power, and then I can use the arrow, and I can just go up and highlight that, and then press enter. And then that whole thing comes in here, and then I press enter, and I get that, right? Does that make sense? Yeah. Even better would be to do this. 120 times 0.5 to the power, and then just plug in 7,000 over 5770, right? And if you plug all that in, then it'll be most accurate, right? But regardless, we're going to round it to the nearest. I'm actually going to ask you all to round to the nearest gram anyway. So you should get about 52 grams. But there's several ways of calculating it. But this last way would be the most accurate because you're doing everything all at once in the calculator, right? Alright, so did you figure out it's about 52 grams? Now, does that make sense with our table? Because after one half-life we had 60. After two half-lives we had 30, right? And our 7,000 years was about in between here, wasn't it? And which is about 1.2 half-lives. And that was 52 grams, right? And that all looks nice, doesn't it? Because the 52 is between the 30 and the 60, right? Does that make sense? Okay. So let's do 13,000. 13,000 years. And how many half-lives is that? And then how much have we got left? Well, let's start with the half-lives. How many half-lives is 13,000 years? Good job, yeah. So we look at our table here, and well, it's got to be between 2 and 3, because 11,000 was 2 half-lives, 17,000 was 3, so it's got to be 2 point something, right? And if we go 13,000 divided by 5770, we get 2.25. So yeah, about 2.3. I'll just say it's about, you know, we'll say approximately 2.3. Good. So, and that lines up here, because like 13,000 half-lives is in between here and here, and that's about 2.3. So how much have we got remaining? Right. And let's see if we can do a good calculation where you're using that big long decimal there. And the most accurate way to calculate it, by the way, everybody, is 120 star 0.5 exponent, and then put that calculation inside a parenthesis like that. Which is, it's roughly 120 times a half to the power of 2.3. So it's approximately that. Yep. And I'm going to ask you all to round to the nearest gram anyway, so that ends up being 20. What did you get for that?